Hi, and welcome to ENGPHYS 2018 test prep. For test number 5 in 2018, we're going to look at the second part of test number 4 from 2017 for this question. So this is going to be solving all of the information from this test. This occurred at the same time as test 5 this year. So what we're going to be doing is looking at figuring out how to deal with this kind of a distributed load, which is written like this. This is a way to show there's not how much force is on this thing, where there's sort of more force over on the left, but it's not at one particular point. It's kind of distributed across the entire member DE. You draw that with this shape like this. It could be one that's flat across if you're trying to say that it's even. This shape is showing you that there's more force on the left than there is on the right on this. And locally, the force is 200 Newton per meter over here. So you'd multiply that by like 1 centimeter and get 2 newtons in that 1 centimeter on the left. And then in the middle, it's like it would be 100 because it's a linear function here. So if you're halfway along, you've gone halfway down towards the other end, which is 0. So we've got we would have 1 Newton in a centimeter across the center part, and then there's 0 newtons in a centimeter at the end. So that's just telling you how you would have a load that's distributed across the top like that. Okay, so what we're going to be doing is trying to figure out first what the X and Y components of the reaction force at point A and the tension in the cable BC are. So this is just going to be dealing with the distributed load. There's nothing else that's really new or that different about this besides that part. So we can copy this, jump into Paint here, which inserts a lot of extra JPEG by doing it that way. No worries though. And we'll just grab the color palette with that button up there. If it disappears on you, no big deal. And draw some forces here. So let's use red for that. We're going to have from a pin joint, an X force, a Y force, and another force that's going to be here in that direction, in the direction of the cable. Okay, so that's it for the free body diagram. We can copy that and then put it back over in the main file and then work with this in order to figure out the reaction force. So what we need to do is write out some kind of a function for the distributed load here. And because it's a linear function, I'm going to say that is 200 times 1 minus x over 4.5. That's going to work. So as we move 4.5 over to the right, we have to have decreased from 200 down to 0. This does that, and it's linear. So that is putting in that is the correct function for this. Okay, now that we've done that, we can type out our net force and torque equations for the entire body. So solve. In the x direction, we've got ax minus cb times cos of, let's make a variable for that. We're going to type the angle twice. So 30 over 180 times pi, cos of q, ay plus cb times sine of q minus 100 newtons at the end, minus the integral of w, x equals 0 to 4.5. So what we did there is we said w is telling us the local force per distance, and if you want the total force in the whole thing, then you would just add up all the little bits of force. So at element of thickness dx, we've got w times dx, so you add up all those w times dx's, and that's the same as integrating w dx over the whole thing. Now for the moment equation, for the net torque, let's say about A, because that'll eliminate both of these forces, we have a torque going to the, making this pivot to the left about A, so that would be a counterclockwise rotation around that pin of CB times 7, or 7 times CB times cos of Q, the X component of that. And then we've got some torques going in the other direction. So we have 100 times 4.5, or 4.5 meters times 100 if we want to be consistent and write the distance on the left part of this. So 4.5 times 100, that's going in the other direction. That's from this one. Again, only caring about the horizontal distance. we don't need to worry about this distance from A to E directly, and then the sine of the angle between them, that's the same as using the perpendicular distance to that force. Now the other thing that we're going to have is similarly minus the integral of W times X from X is 0 to 4.5, because adding up a little bit of force component was integrating W dx. Adding up a little bit of torque component would be integrating X times W dx. So that should do it. Okay. Next part, the question asks us to draw a shear force and bending moment diagram for ADB. Now, in order to do this, we're going to need to figure out what the reaction that DE places on ADB is. And there's a couple of ways we could do this. We could look at just the member ADB and see what would place it in equilibrium, or we could look just at DE and see what would place that in equilibrium. Let's do a little bit of both, actually. So what we'll do is we'll take this thing and we will kind of move it off to the side a little bit. Maybe we'll put another white rectangle over here so it doesn't look quite so weird. And there. Now we're in a position where we can draw the reaction forces on each side. So at the junction in here, we really will have a force that's applied from this section on this section, which is a shear force down. So we'll call this maybe dy. And we are going to have a force in general, which is an x-directed force, although this time it's going to be 0, you can see from looking over here. And we are going to have a moment. So before we add the moment, let's look at how these are going to be repeated on the other side. So Newton's third law says the force that DE is placing on ADB in the y direction is equal and opposite to the force that ADB is placing on DE in the y direction. So that would be this right here. That's the same dy as this one, and same in the x direction. Okay. So then for the moments, we are going to just grab a different color here. And how about something like this? Curve that around in order to draw our moments there, MD. And we can do the same thing on the other side. So if we are going that way, kind of counterclockwise, creating a moment on ADB, and then ADB has to be creating a clockwise moment on DE. Now, from looking at the picture, you can see that the moment that we've assigned right now is actually in the opposite direction to what the moment would actually be doing over here, and that's not a big deal. That doesn't actually matter for this. So we've got it just is going to end up being negative in the direction we've shown, but that's no big deal. Okay, so that is the setup. So now that we've got that, we can go and write our equations. So we can look at just this side and solve for what the values should be for those reactions by establishing that that's in equilibrium by itself. And this should have nothing to do with the setup that we've got right there. We are going to need to grab that distributed load, but then we can just work in a completely different part here. So we can solve the net force in x would be negative dx, and that's it. As expected, that's going to be 0. The force in y, we would have dy minus the integral of w, x is 0 to 4.5, and minus 100. And then for the torque equation, about d, for example, we've got all three of them are going in the same direction. They would all make it rotate the same way about d, so that tells you right away that md would be in the opposite direction. So we've got md plus integral of w times x, x is 0 to 4.5, plus 100 times 4.5. 4.5 was the distance away. It got cut off with this clip that we took there, but that's still the distance all the way to the end there. Okay. So dx is 0, dy is 550, and md is negative 1125. That one would be in Newton meters. Okay. Now, as a test, we can also go and, looking back at this diagram, try to use this to figure out what dx, dy, and md are. So for that, we're going to go back up to this first example where we solved for the external reaction forces and assign them. Then write out the net force and torque on this body is equal to 0. So let's try that. So we'll solve ax plus dx minus cb cos of q in the x direction. Ay minus dy plus cb sine of q in the y direction. And the torque equation, about A, let's say, we would have negative, or I guess positive, cb times cos of q times the distance 7. Let's again try and put the distance at the beginning. So that's 7 away. And then we've got 1 from dx, and that would be 4 away, but it's in the opposite direction. 4 times dx. And compared to those two, md is in the counterclockwise direction as well. Now it's actually negative, but that's okay. This is going to be dealing with that. So this should give us the same answer for those values as we just got. And at first it looks like we got something different. We got this thing for dx versus 0, but that's e minus 7. So that just is hinting at the precision of Maple for this example, rather than actually indicating that there's a different thing. So the rest of it is correct. We've just got a limit in the precision that we put in. Yeah, so that's a good check. So now that we've done that, we can go and draw some shear force and bending moment diagrams by taking some additional slices of this thing. So the question actually asks us to do it for this part, but let's go and do it for this part instead first. So going back over to our picture here, what we can do is cut it off at, let's say, the right-hand side or the left-hand side. So we'll go back to our rectangle tool, and we'll draw a rectangle on top of that. Okay, and now we've got a slice here where we can assert that there's some internal forces. So let's grab a new color, and we'll label a shear force V. We'll label a normal force N, and we're going to label a bending moment in, let's say, blue there. Okay, so there's our shear force and bending moment construction diagram. This is not the shear force and the internal force and moment diagram that we're going to end with, but this is the one that we're going to use to get it. Okay. So from this picture, now that we've gone and figured out what dx, dy, and md are, we can say that this little piece, a distance x across, is itself in equilibrium. Assign this solution that we just got for dx, dy, and md, and now set up the equilibrium of this part. So solve that in the x direction, we've got negative dx plus n. In the y direction, we've got dy minus int of w from x is 0 to, let's say, big X. That's a different x than this one. And we've also got in the negative y direction v. So what we can do, I think that's it. I don't believe we forgot any of the forces. So then we need the moment equation. We did the x force equation, the y force equation, and the moment equation is going to be, let's say, about point D there. We would have big M is in the counterclockwise direction. So that's the only one in the counterclockwise. Let's sum up in the clockwise direction this time. So we've got MD plus int of w times x, x is 0 to big X, plus v times big X minus md is equal to 0. So let's see if this works. It doesn't know exactly what to solve for. It's got some imaginary numbers there, it looks like. So let's give it that we want to solve for n. See, it's tried to isolate for x rather than, but in reality we want things in terms of x, n, v, and m. Let's see how that goes. So it doesn't actually give us any sort of a solution, but that's okay. Writing it out like this is good to assert to Maple what it is that we're trying to solve, like which equations we're trying to solve, but these equations themselves are easy to solve directly. So we go to here and just say n is equal to dx. Okay, and we can go v is equal to this part of that equation. And here md would be equal, or, oh, I see what I did. This isn't md. This thing should have been subtracting off an m. So let's see if that works. Ah, okay, there we go. So we've got n, v, and m. Still, sometimes this won't actually work. So you can, you could instead just go and manually solve them by looking at the equations and then asserting what they're all equal to. So this should give you the same answers then. Let's not suppress the output to that. Okay, n, v, and m. All right, looks good. And that's fine that it has all this x dependence because you expect that these things are going to be different depending on how far along this, this bar we are. So now we can plot them. And we're going to be saying from x is 0 to 4.5, and we're going to add in a legend just to say what symbol is what. Okay, so you notice n doesn't show up at all because it's just 0. V is this one, and m is that one up there at the bottom. So m starts at this value of md at the left, where it's got to be equal to that. You can imagine if you take x all the way really small, then m's just cancel. The v has to directly be equal to dy at the left, and it looks like it is 550. And it decays down to the value of that 100 newtons on the right, because that's the force that is applied at the right, so the rest has to be responding to that. And the moment increases up to 0 because that's the moment that's applied on the right. There's no moment applied on the right-hand side of this complete object. Okay, so that's the shear force and bending moment diagram for this object here, this this extended part, remember DE. But we would also, the question actually asked us to figure out what the shear force and bending moment diagram was for ADB. Okay, so let's give that a shot. How to do that is, again, by slicing this object, except this time we're going to have a bit of a piecewise setup. So let's take a slice maybe there. And grab a new sheet here. And what we can do is label out the shear force and bending moment on this part. So let's go one arrow, 2 arrows, and we'll also, and we can label those. So that would be the shear force and the normal, and then we'll also have the bending moment diagram. The bending moment around the top, something like that. Okay. So if we take this piece and assert that it's in equilibrium from the AX and the AY and the DY, DX, and MD that we've got, working now in the other part of the code here, we can get the what the M, V, and N have to be for this part. So Again, starting out with solve, ax plus v plus. Now, we only want dx to be added if we are at a y value, let's say, which is larger than 4. So a couple ways you could do this. You could say plus dx times piecewise y is greater than 4 and then a 1, otherwise 0. Or you could try piecewise y is greater than 4 dx, and then that's only going to be added in that way. That's fine too. Okay, what else? In the y direction, we've got ay minus dy plus n, but again, we only want to be subtracting dy if y is greater than 4. And also for the moment diagram, the torque equation, that is, the net torque about A is equal to 0. So we are going to have M. We are going to have in the other direction minus V times big Y and minus dx times 4 times piecewise y is greater than 4. And we want to solve this for v, n, and m. Let's try. Doesn't find it. So this is the situation we were talking about below. No problem. We can just go and manually solve these things. It tends to break down a bit with the piecewise functions. So that would mean we've got v is equal to negative that thing. From the second equation, when you move it over to the other side, n is equal to negative that thing. And m would be equal to negative that thing. Okay. So that it deals with no problem. But you see, again, it's piecewise on this, and that's part of why we couldn't just solve it with the solve command, because it has no idea about what big Y is. So still, once you've got this, you can plot them like normal. Because we used the same variables, we can actually just flat out copy this other plot expression, and it will do different behavior up here with these different functions assigned. Ooh, well, in theory it will. Let's see, what messed up? Oh, we changed the variable from x to y, and we want to go up to 7 this time to get to the top. Now at the top, this should be limiting to a moment of 0. So it seems like something has gone wrong right away. When we're at a y of 0, we should have a moment of 0, and when we're at all the way at the top, there's no torque, there's no point torque applied at the top, so that should also be going to 0. So let's see exactly what went wrong with the torque expression. We were saying that the net torque, we've got it spinning one way from m and a totally different way from v and dx. So it was m minus v times y minus dx times 4, that distance, as long as y is bigger than 4. Aha! So although we added in the force parts, dx is actually 0 anyway, so this part is not the confusion. What we didn't do is we actually forgot about a moment, so we didn't add in this md there. So we would need to add that as applied there, which means inside here we'd add in md. And now, yes, okay. So what this is saying is that the moment actually goes down to 0. You know, what happened is, so now it's wrong at the other end. Why is that? Well, because MD only gets applied when we're at a Y that's bigger than 4. So what you can do is say, add in plus md minus dx times 4 to this whole piecewise thing. And now it's behaving properly. So we've got a moment that's 0 at the bottom. And then after we pass that 0.4, then the moment has to increase a lot to counteract this MD. Now you think, okay, wait, after MD gets added, then wouldn't this have to decrease to keep the whole thing in equilibrium? Well, no, because MD ended up being this big negative number. So the moment that's applied from DE is actually in the opposite direction to what's shown here. Positive in the opposite direction, negative in the direction that we've got, which is what's canceling, which is why this moment has to go from a negative one at the bottom to a much more positive one when we pass this point D here. Okay, so that is now making sense. It's a diagram that we can stand by. Now, when we made these plots for the shear force and bending moment and internal normal force, what we did is we just looked at the bottom part of this entire object. Instead of that, we could have looked at the other side, so the top side of the object like this. And here I've gone and drawn Newton's third law of force and moment pair. So a moment going the opposite direction of this moment. This one is spinning counterclockwise. So if the top part is making the bottom spin counterclockwise at this junction, then the bottom part must be making the top part spin clockwise. And same complementary things for the shear force and normal force. And we could have used this to write the forces instead, and we should get the same answer. Let's just go ahead and put this on top of that one so you can see those all laid out like that. Okay, so let's try that. Let's go up here and take the first part of this. And we will now try and redo those equations by only looking at the top part and see if we get the same answer. So let's get rid of that bottom part so we don't get distracted. And yeah, so what variable should we use here for the length? We can now start y at the top going down, maybe? Or maybe let's call it a different variable. Let's call that maybe, I don't know, z from the top going down, just so that we can later refer to z. So yeah. So we could type out the equations again. The x force equation is negative v minus cb cos of q plus dx as long as z is greater than 3, meaning that we've moved down more than 3. The y force equation would be negative n plus cb sine of q minus piecewise if z is greater than 3 dy. And the moment equation would be, let's add up the moments going in this direction. So, and we can add up the moments about the bottom. The distance from the bottom to the top is z. So if we do it about the bottom this time, rather than about the top like we were doing in the last examples, then we don't have to include v in the moment, but we do have to include CB, and it gets a little bit trickier with that. So let's have a look here. We're going to say that the moment about the bottom, we've got CB times cos of Q times Z, and we've got minus M plus that, as M's going in the opposite direction, and we've got something if z is greater than 3, an additional moment term. So we're going to be adding in md, which is in the direction that CB would spin it. So that's what we're doing in the adding direction for this part. But then we've also got a moment created by dx. And how far away is this from the bottom? Well, it's if z's the whole thing, it's z minus 3 away from there. So that's minus because it's making it spin the opposite way about the bottom as md is. So that's minus dx times z minus 3. Check more z, meaning more kind of a lower piece there, and we've got more moment from dx. Okay. Now this is, again, not going to work, probably. Although, because we didn't couple this in with v, it might be explicit enough that it can solve the whole thing. Let's see. Nope. Got confused. So let's just go and solve that explicitly. So v is equal to, by writing them all as negative, it's easy to copy and paste the other side of the equations here. N is equal to that. And m is equal to this. Now we can try and plot the same thing as before. From z is zero to 7. Let's try. So if we go and compare to this thing that we got earlier, then the new version looks pretty similar, but is actually the opposite. And that's not surprising because we defined z as the distance from the top down, where y was the distance from the bottom up. So we could make a substitution actually, and convert from the z equations into y. How could we do that? Well, by substituting in that z is replaced with 7 minus y in these equations, then we should be able to, this should directly rewrite them in terms of the equations for y. So let's see. Yeah, so how did we do that? Well, at the top of the thing, we are at a depth of 0. So y was the distance from the bottom up. So that's how you can tell the relationship between z and y is z is 7 minus y. We used the subs command, which is going to go directly in and then replace everything that's a z with a 7 minus y in this expression. And that will put all of the terms that we found in terms of y, so we can then check that it is exactly the same diagram as we had before. So it doesn't matter which side of the thing you look for, you should determine that the internal shear force and bending moment is the same as long as you use the correct application of Newton's third law to translate to figure out what the forces here would create on the other one in terms of equal and opposite reaction forces. So that's it. Hope you had fun. Thanks.